Hi, so my name is Claudiu. I'm an engineer working for Atigeo. We're based in Bellevue, Washington, and I work with an amazing group of engineers from Romania that made all the demos you'll be seeing soon possible. A special thanks to Team Omega for working hard to wrap this up. And I want to ask the audience, what do you prefer, slides or live demos in a presentation?
Yes, live demo.
Live demos? What about the crashing demo? Let's hope it doesn't happen. Yeah, I prefer demos myself. And so here's the agenda quickly. We'll go over xPatterns and explain the logical and physical architecture. And then we'll do a lot of demos. And then we'll leave some room at the end for lessons learned with Cassandra in the past 4 years. So what is xPatterns? It's a big data analytics platform that provides tools and APIs for engineers to build end-to-end big data intelligent applications. So now we express that in 3 powerful verbs: connect, discover, and act. So the connect is the infrastructure provided, the big data infrastructure with all the tooling from provisioning to operations. Allows you to build things like an ETL pipeline or a data warehouse. Then we have an intelligence layer, the discovery part. It's more for analysts and data scientists so they can do their modeling and building model, training them, publishing them. And then we have the act part, the application layer, where we provide APIs that allows them to build, allows application engineers to build user-facing applications. So where do we use Cassandra in this ecosystem? So our platform, imagine like I talked, the infrastructure allows you to ingest data from external sources into a compute cluster where we build a data warehouse. In the compute cluster, we have the typical Hadoop and Hive. And the last year, we upgraded that stack to Spark and Shark, Spark SQL now. Mesos is resource manager. And Tachyon as an in-memory distributed file system. So these are co-located side by side. There's also Aurora that we use as another framework that runs under Mesos. It's not mentioned here. All the data that's being ingested in the data warehouse, HDFS and Tachyon, it's also geo-filled over through S3 buckets and different different EC2 regions. Then all the machine learning, all the data warehouse operations are performed in this cluster. Whenever we want to build application, expose those applications to end users, we separate workloads and we push data from the warehouse into Cassandra mainly. Cassandra is our main real-time database. We also have solrCloud and SQL on the side. The talk and the demos today are about, obviously, Cassandra. And in the process, not only we build an efficient data model in Cassandra out of the data in the warehouse. We also geo-replicate that in real time over an IPsec tunnel, another region, so we have a multi-DC ring. And we also generate APIs, low-latency, high-throughput APIs that are also geo-replicated using AWS's Route 53 DNS service, which really directs client requests to the closest data center. Obviously, here on the West Coast, will be sent to the West Coast data centers. And that's part of the demo. We'll show how we ingest data, we do a data transformation pipeline, we create a data warehouse, and then we publish that data to Cassandra with APIs on top that are ready to run. These APIs have 3 ingredients. They're geo-replicated, they are instrumented, and they're monitored. And that just comes out of the box from the xPatterns tools. But let's just switch to demos now. So this is the xPatterns management console that allows all this to happen. You see the 3 verbs: connect, discover, act. So connect allows us to ingest data, and then transform it. We'll do a bit of discovery to discover the warehouse that we build on top of that data that's been ingested. And then ultimately will export to NoSql. I'll briefly go through the first set of tools. The ingestion tools, now they all use Spark behind the scene, connects to S3 or SFTP. You can run your jobs, you get the full log, execution log of what happens behind the scene, which means decompression, the backup, the geo backup, moving data over to the other data center, and so forth. At the end of it, your files will be readily available. Our data store right now is HDFS. We're adding support to directly streaming data into Tachyon as well. That's work in progress. So that's the ingestion piece. Then once you have the data in HDFS, you can build your data pipeline. And we enhanced Uzi, part of the Hadoop ecosystem. And we provided, in addition to their, to Hive, Shell, SSH, those type of actions that Uzi provides out of the box, we added Spark, Shark, and email. So this, again, it runs, sends all the logs in real time to the console through WebSockets. Engineers provide, they create Spark jobs or SQL scripts. We log, we execute that in a managed fashion, and we push the logs back to the console for debugging purposes with all the details behind the scene. So that's the data transformation pipeline. Part of the pipeline, at the end of the pipeline, is creating these tables in Shark, right? You can use Hive or Shark, either way. And we built a Hue-like tool that allows you to explore your data, your warehouse, your tables in the warehouse, with their structures. You can quickly build queries. You have a query editor. You have the results. You have the query history. For each query, you get the results and the executing logs behind the scene. So that's available. With this warehouse, they're also exposing data that's being stored in the Tachyon, right? That's our in-memory distributed file system. All it takes is creating a table and suffixing that table with _Tachyon, and that Shark will push that into memory. And then you can start querying it. So I'm not going to insist too much on these tools. What's behind the scene is an open source project. I have a link at the end of my slide. We call it JAWS. It's our HTTP Shark server or Spark SQL server, depending on what's the execution engine behind. I'll insist more on the export to NoSql tool. So once my data is in a warehouse, if you remember I'll go back to the architecture diagram. We have the data in the warehouse. We processed it. It's ready to be exposed, right, through APIs. What this tool will do will connect to any data in the warehouse and push it to Cassandra and also generate these APIs behind the scene. It does all the geo-replication at the data store level and the publishing of the instrumented and monitored APIs. What we're working on right now is also enhancing this tool to provide support for connecting to data sets in Tachyon. They're already in memory in this cluster, but does not expose yet through these tools. So now you can create a test job. Then you're allowed to pick a database and a table. You're creating the first job template. This allows you to browse that database you selected, pick any table from here. We're not, like I said, we're working on supporting Tachyon, both tables created through Shark, they're stored in Tachyon, or really Tachyon files, they're stored in the Tachyon memory with managed schema on the side. So once you created that, then all you have to do is drag it here to create a mapping. So we're mapping data between the warehouse and NoSql. Looks like we have a bug. In the process, we're supposed to pick unique keys to specify what's the unique key so we know how to model that data in Cassandra. You can do field transformation, change types. There's a few field transformation operations available. And let's actually do that and save it. Pick one unique key. And you can drag this mapping now here to create APIs. And these APIs, another bug. So these APIs will need the read access patterns. The application engineer knows best what data to read and how to read it. So now using the mapping, they'll provide, that's the bug I'm talking about, that's why the drop down is so long. They'll have to pick a lookup field, and they can do sort by today. And we're working on adding group by and filter by, which with NoSql, it's not trivial. At the end of this job run, this is the signature of the API that's going to be generated. But what I'll do, I'll go back to a pre-created job. This is a data set downloaded from the national provider. There's a database with all the providers in the country, doctors, hospitals. And we created two mappings. One that's going to move over only a subset of the fields, which you'll do most of the time if you want to create some fast lookup APIs, providing an ID of the provider and getting back the name. I also created a mapping that allows you to get back the entire data set. What we do behind the scene, we denormalize and we create views for each of the data set. So starting from each mapping, we created two APIs. One is lookup by name and sort by API, and the reverse operation, looking up an API and getting back the names. And the others for the partial will get the subset of the field. So just by doing this mapping here, I'm going to generate 4 APIs. And let's run this job to see what we get. Each of these tools that I showed, they use Spark behind the scene, and they allow you to specify the level of parallelism. How many Spark cores I want to use on the cluster. And in this case, I know I have this many cores in the cluster, I'll use everything. And my job starts. So what I get is, again, execution log with all the details. Now the Spark job server that runs that context, we're running under Mesos. I'll show you the Mesos console in a second. The execution details for the Spark job. What we do behind now is, we connect it to this database table, DemoDB table MPI all. We're finding the underlying HDFS file, and we're sizing it. And we need a sizing of the data in HDFS so that we know how to build that efficient data model in Cassandra. We'll never, imagine you have 1 billion records on one table. You don't want to just transfer that into 1 billion Cassandra rows, skinny rows. That's not going to yield a very good data model. So what we do is we try to maintain the row size in the 50 megabyte range, which means we're grouping those multiple rows from the warehouse into one bigger Cassandra row. So then we do column slicing to get to my actual entity that I'm transferring. So that's done behind the scene, all the validation, checking for null fields, for unique values, whatever I specified in my mapping. And then I'm starting my export, into a column family that's created behind the scene. In the Cassandra ring is geo-replicated with the APs. So the job started to write. What I also get is an instrumentation dashboard, I have 4 slaves in the Spark cluster. For each one of them, we emit metrics and we capture the throughput, average latency, expressed in microseconds. So we're talking about 2 seconds, spikes, 4 seconds here. That's the latency reported by the Spark cluster. Most of the time is spent in network I/O because we're moving data from one cluster to the Cassandra ring over the network. And also the total items and total calls, they're being transferred. There's also a new feature here called the retry count, which is if you have a big enough cluster, Hadoop, Spark, doesn't matter, you'll have the same problem. In a small enough Cassandra ring, you might be exercising too much load on that Cassandra ring. And at that point, Cassandra will start dropping those requests and sending back exceptions. So what we do on the Spark side, we capture those exceptions and we emit a metric. We're retrying that at 1 second intervals. But we're also exposing that in this dashboard. So since it's 4 slaves versus 3 nodes on the East Coast, that's not a mismatch in capacity, so we'll never see these retries here. But normally if you saw them, that means you were maybe too generous with that initial level of parallelism that you specified when you started the job. So you can cancel the job and restart with less. And in the future, we want to do this auto-throttling mechanism ourselves behind the scene. But it gives you that kind of control. So at the end of the job, the data is being transferred, and there's 4 APIs that have been generated, and they're ready to be used. And we can test them out immediately. We can look at any of them. So that's my API definition. I have a lookup API, and I have a list, right? You can pass in a value, an API, and get back the name, or you can iterate through the entire data set that was transferred. And you have your, you have the full signature and an actual call, now with all the headers, with the request and the body, with data behind. But we also have a data browser here, just to quickly test what's been transferred. Can you see that? Yeah. So now you can page through that. Let's find some value to try it out. Some MPI value. Okay. So there was a hiccup in the balancers. So let's pick one MPI value. I'm going to copy that. I should get back Kish Brook, right, from Colorado. But this is my MPI, right? So I can now test my API passing this value and query it. So this is the generated API. Is the fact that it goes to service.xpatterns.com, it means it goes through that DNS service and it's geo-balanced. So it's going to end up on one of the clusters, East Coast, West Coast. For us, it's West Coast. It's here on the West Coast. You get back your data, and that's how you pretty much ended up with an API that's geo-replicated. I also said that this is instrumented and monitored. So let's see what that means. Let's see what instrumentation means. So I'm going to go to the monitoring tab, and I have my instrumentation dashboards here. So what you see, I have 4 Tomcats. Well, the 176 ones are from the West Coast. The 1002 are on the East Coast. And this will tell me, no, I had the average latency for the call on one of the West Coast Tomcats was 152nd milliseconds. And you have throughput, like items per second, total calls, and global latency. So this is a fairly new feature, just added. Probably needs a little more work. But now we can test this out, accessing those APIs on the East Coast directly. And normally I should see some traffic here popping up very soon. Yeah, so it just showed up. So a node on the 199, 60 items from the East Coast API were retrieved to this API call, and only 2 from the West Coast. So now the API you just created and just published is now instrumented. What we also do is also monitor these APIs. So we use Nagios for that, which will monitor the entire clusters, all the clusters actually. And if I go to the front ends, the Frontend Group, I have 2 servers on the West Coast. These are the metrics. You have the classic disk I/O network, CPU, memory, and we set up alerts here. When we exceed certain thresholds, we're being alerted through emails. You have Hector metrics. These are your Cassandra clients with everything that they expose. And we have the xPatterns API metrics, the same metrics you saw. So this is the JMX bean that's really instrumenting that API call, read data. And obviously, we can set up alerts here for various thresholds again. So let's talk about the Spark part. So I said we're running under Mesos. We have a cluster of 4 nodes, 4 slaves, each one having 32 cores. So it's a total of 128 cores, and this much allocated memory across the cluster. So we're running multiple frameworks here. It's Hadoop running side by side with our two RESTful servers on top of Spark SQL or Shark or JAWS, and we have two Spark job servers. So everything can be tracked here. Our export jobs ran here in coarse grain mode, and it finished, wrapped up after the job. You can get more logs from the actual execution logs in Mesos. I can look at the things that happen behind the scene. Any exceptions that were caught by Hector, and there are some. Yeah, so Hector, there's a few warnings from Hector. Now Hector is the thrift driver wrapper, I should say, the Java client, which does its own retry and failover. So those we'll want to capture in the future as well and show in that instrumentation dashboard. So you have full logs of what happens behind the scene. We also use Ganglia for monitoring all the clusters, including the Cassandra East and Cassandra West. It's a load on the CPU, memory, disk I/O, network I/O. This gives you a nice graphic representation of the clusters behind. So while the transfer was run, there's also a Graphite dashboard that allow us to instrument Cassandra itself. And we have pre-created dashboards here that will look at the write latency. So let me minimize this. This is what happened in the last, Let me go back to the write latency dashboard. I'm going to do the last 5 minutes. So we can see that maybe I should do 10 minutes to see the full record of the latencies as reported by Cassandra. So we had activity on the 3 nodes on the East Coast. Right, we're only writing to the East Coast, but that data is being replicated in real time to the West Coast cluster, West Coast ring. And we're seeing 40 microseconds in terms of latency. If you remember, the latency on the Spark side were 2-4 milliseconds at the most. So that's the kind of latency we see in this transfer. So what else? Okay, so this is pretty much the export to NoSql tools, and I'll show you an end user application that we built using these tools. That's a demo environment. This is an actual production application that we were allowed to show. It's called a referral provider network. So you saw that we transfer data, all that provider data set. We're also using a customer-owned data set that has 10 billion medical and pharmacy records. And we extracted, through ETL and data warehousing operation, we extracted all the relationship between providers in those claims. Like starting from a provider, all the referring providers, or downstream and upstream. Who this provider referred to, and then a grouping by specialty with claim counts and the total charge amount, and the downstream relationship. So let's see the demo of that. So we're going to pick a physician and a provider. Submit. By the way, this is a dashboard that just uses the data that's exported in Cassandra. So it uses those APIs on top of Cassandra, nothing else. It's roughly 1.8 million providers that were extracted from that 10 billion record data set and 50 million relationship. So now starting from that provider, we have a grouping by specialty, internal medicine, I'm not going to pronounce that. Neither that. Oncology I can pronounce. Pulmonary disease. So you have all these specialties, and within each specialty you have total number of claims, patients, 3 providers referred, and the total charge amount. So how is this useful? Now the customer asked for a graphical representation of all the relationship of the providers for 2 reasons. One, maybe to detect fraud. If you see these highlighted providers are in-network providers. They want to know if their providers are referring to providers within the network, because that's the requirement. Maybe they'll find somebody here, which is maybe a cousin or somebody who shouldn't be referred to. But it can also be used in a different use case to find this company is acquiring networks. They want to know what are the reporting provided in other networks so they can go and acquire those as well. So they can enhance their own network. So two good use cases. All these stats were pre-computed in the warehouse through Shark. A lot of this data was exported through these APIs into Cassandra. So all it does is just extremely fast key lookups. And if you have no good JavaScript engineers with D3JS skills, they can build something like this. So that's just an example of an application built on top of xPatterns. So starting with ingestion, transformation, data warehousing, exporting to Cassandra, published APIs. Again, these are geo-replicated APIs, and the actual dashboard. Okay, so that's my my demo. Any questions so far? So I want to talk about the lessons learned. We started in 0.6. We're still using Cassandra, obviously, today. Some of the things we learned the hard way. We have to synchronize all clocks. Now, we use NTP on both servers and clients, right? That's mandatory, various reasons. What burned us is schema disagreement. So whenever we transfer these, we create these column families in Cassandra, with each job run, we're creating column families, and they have to be synced across the two regions. A lot of times we would see schema disagreement, which would prevent us from performing any operations on those column families. So what we learned is that before we create and delete any column family, we create a lock in Zookeeper so that we make sure that there's only one of these operations performed at any point in time. And before we create that and delete it, we also synchronize. So we use something equivalent to no-tool reset local schema that's going to go to every node and make sure that it synchronizes the schema before anything can, before we make further schema changes on that particular node. We learned that in order to avoid out of memory, especially in high throughput, write throughput scenarios, we're minimizing the number of column families. Cassandra just doesn't like a large number of column families. I'm not sure it's been fixed today. It's not even recommended to create a large number. And the fact that we still use thrift, and because we started in 0.6 and Hector, essentially there's no schema. So you have the freedom to store any rows and anything in those columns, and mix any type of data in just one column family. So that's how we learned how to mix multiple data sets in the same column family to avoid growing this number. Something that you should be aware of, it happened to us, dropping a column family before emptying it, which means the truncated and compaction, just rendered the ring useless. It happened to us twice, and now we learned that lesson. And right now, before we remove something, we make sure that we truncate that first. Cassandra gets into a state where it's trying to load files that shouldn't be there anymore, and it gets into a deadlock. Monitor, instrument everything, and do automatic restarts. Cassandra will crash very often, but we have scripts to restart the daemons automatically. Consistency level 1 is best for our use cases. Now, you saw all our write operations are happening overnight. So we can afford to just write the data, and then all the dashboards, all the read operations are performed for a user-facing application during the day. So we have enough time enough of a distance between these two, the batch job, the transfer, and the actual reads, that really we can write and read with consistency level 1. If anything happens in between, we have monitoring, we can react and then restart servers and so forth. But CL1 will give you the best performance. Use the key cache. We use NAPI for compression and vnodes. One more about data modeling. So what we learned all these years is, again, we have high throughput write scenarios and read-intensive scenarios as well. In order to avoid out of memory, we learned that we should keep that rows in 50 to 100 megabyte size. Not too small, not too skinny, not too wide. Now, pretty much you want to reduce the number of rows. Like I said, 1 billion rows is not going to work too well in Cassandra. That means now pressure on too many rows, too many calls over the network to grab more data, pressure in memory for the Bloom filter, for the key cache. And obviously you have less, reduced network I/O when you have less rows. On the other side, having rows that are too wide can create inefficient compaction and can create hotspots. So that's why we pick this particular size. That's why when we move the data from the warehouse, we always size it. We look at the data in HDFS, and then we count records, we look at types, and then we look at the data, the actual file sizes, and we compute that. So that we can then do the 1 billion to 50,000 rows in Cassandra transformation. And what we learn is that we're doing our own custom serialization. So instead of those entities that we create, provider with name, ID, title, address, what we do, we serialize them on the client side into a byte array, and we only store a byte array through in Cassandra. And that gave us almost 40% performance gains. Even though only applications can now read that schema, right? So you have schema, right? Like you're reducing the interoperability with other applications, but really what we care for is maximum performance, since we manage the schema through our API definitions. Yeah, and that's my talk. Questions? So the question is, what's the danger in having the rows too skinny? Skinny rows means a large number of rows, right? 1 billion rows, that creates all sorts of pressure. First, just if you want to retrieve multiple entities, it's very likely you end up making multiple network calls. Now maybe your data is going to be spread out across multiple nodes. If the rows are wider, there's a higher chance that one row can be, because it's in one wider row, your entities are serialized in one big row, and it can end up in only one physical node. So retrieval might mean just one mem table scan or one disk scan on just one node instead of doing multiple network calls and in a scattered gather pattern. And also, there's a Bloom filter which are stored in memory. The more rows, the higher the size. Mem table, metadata associated with rows, especially if you have distinct columns and you use the old way of storing column name and column values. Sometimes metadata is higher in footprint than the actual data itself. So that's why we're very stingy with that footprint. Like we store columns, we store column names in only 1 byte, and we do our own serialization in byte arrays. So they all contribute. Compaction, you help with all these data structures, memory, just make it more efficient. It requires more work, obviously, on the developer side, but we chose to sacrifice developer happiness for the reduced operational cost and performance. So.
I apologize for arriving late. When you store your data, are you storing byte strings? Is that correct? What you said?
So the question, if we're storing data in? Yes, and when we move over to Cassandra, we're serializing our entities into byte arrays, and we're storing just small blobs.
You're storing blobs?
Yeah.
Are those blobs reserialized into objects or something like that?
Yeah, when we read the blob out of Cassandra, and we deserialize on the client side.
So, okay. All right. Amigo has kind of the same feature. I'm a Hector, we're using Hector 2 as a result of being an early adopter 2 years ago. Thank you. What we do is actually, I have a JSON string, I'll compress it, and then serialize it to bytes and store it.
Yeah, you might be looking at more efficient serialization. JSON it's expensive to parse. There's other formats. We do our own custom, but you look into things like cryo, for example, that Spark uses both Java and cryo, the cryo serializers. And if you register classes with cryo, the footprint of the binary output is small, and it's efficient it's efficient for storing. And we use that, for example, when we save. We have data set that we're saving into Tachyon, our in-memory distributed file system, this little icon here. We store that with cryo, and then we save in sequence format, both in memory and disk. So JSON is not your best, doesn't yield the best enough footprint.
Do you expose a SQL?
Yeah.
Sorry, the voice from above.
Yeah.
Do you expose a SQL query layer on top of this at all? Have you looked at doing that, or is it just through the REST endpoints?
So we have the REST endpoints for the data that's stored in Cassandra. And if you remember, on top of the warehouse, we have Spark SQL or Shark and Hive side by side, and Tachyon files. And what we do is, if you go back to the Warehouse Explorer in the discovery part, so we have our own RESTful Spark SQL / Shark server, which is an open source project. The link is over there. No, GitHub Atigeo. And that fuels this UI. So yes, we're running SQL queries, I should say HiveQL queries, through this interface. And depending on the engine behind Spark SQL or Shark, that works on data that's stored by Hive or in Tachyon. But we only do that in the warehouse. We're actually working on exposing data in the warehouse through building OData APIs on top of this data in the warehouse, so that we can do BI dashboards directly from data in the warehouse without going to NoSql. But now we're talking interactive latency. Could be seconds, could be tens of seconds, minutes, right? When you do run large queries in the warehouse, albeit with Spark as fast as it is. But if you want really low latency, high throughput, we're talking sub-second latency, then we're better off exporting to Cassandra. But when we do that, we pick exactly how many rows. Now imagine you have 1 billion records with 100 fields in the warehouse. It's very likely that no dashboard that you're building is going to need to expose all the fields and all the 1 billion records. Now, so then through this tool, you're allowed to pick which fields in the mapping. Now you can hide. For example, here I was able to hide title and address. So I'm only transferring these two because all I need is to look up an API, get back a name. That's going to be a faster API than retrieving the entire set of 100 fields, for example, and then discarding them, right? So that's why what's key is that the application engineer defines the read access pattern in these mappings.
Question. So look at the diagram flow again, like the architecture diagram. Do you guys do stream processing for input? I saw like Kafka over there. Is that the way you guys do streaming? Do you guys support streaming input for data, for external data, such as like if you think of like Twitter feeds or something like that, that continuously streaming data into your storage?
Yes, the answer is yes. We have two types of ingestion. The poll ingestion, which you saw the tool that connects to external data sources, and you have a Spark job that is triggered and it scheduled and connects and pulls data in. We also have push ingestion APIs exposed. They're storing data into Kafka, and then there's a Spark streaming job triggered that's going to pull data out of Kafka. But that Spark job is running in the cluster alongside other analytical workloads. Could be machine learning algorithm, could be other batch jobs, all managed by under Mesos. So we do use that. So we have these APIs that are published. It's just an API that's published. There's no tool there in the UI to show you that. But it's a very good question, yeah. Yes.
The ingestion from the customers, right? I see you mentioned SFTP S3. Do you provide also like some sort of an agent that sits there on one of their boxes and just keeps shoveling data to you, or?
So that's a very good question. So in the poll ingestion model, out of the box today we only have SFTP and S3, and HDFS is being worked on. what we were doing is integrating Talent, which now has an advertised 450 plus connectors. And then we want to be able to configure Talent jars, really, applications to consume data from external sources. So we rely on a Talent application to be written, but then push to us, and then we manage the execution of that Talent job. So that's how we're going to support multiple data sources. But most of our customer needs, they just narrow down to files in SFTP or S3. So, and now more recently HDFS, like another HDFS cluster. So we're building support for that. And I guess I didn't mention this. All traffic goes to these two servers here, JAWS, which is our HTTP layer on top of Spark SQL or Shark, and our own Spark Job server. And both of these are open source projects on our GitHub. You're welcome to download them and use them and contribute back. But what we did with the Spark Job server, we took Yala's job server, and we solved a problem in Spark that hasn't been even solved today in the Spark core, which is running multiple JVMs, multiple contexts in the same JVM. Like if you have a web server, you're triggering two different Spark applications. They will not run. At some point, if both of them are trying to write to HDFS, one of them will fail. So we isolated now these drivers in our Spark job servers in different class loaders, and now we can have different Spark applications running through the same server, loading their own dependencies or different versions of the same dependency.